Now let's look at how Galileo championed Copernicus and cemented the sun-centered solar system. He is considered the first modern experimental scientist. He overcame a number of objections to the Copernican view. Three particular objections rooted in Aristotle's view of physics were the fact that the Earth could not be moving because objects in the air would be left behind, the fact that the non-circular orbits are not perfect as the heavens should be, and that if the Earth were really orbiting the Sun, we'd detect stellar parallax, or the seasonal shift in star positions and relative brightness as the Earth moves in its orbit. To overcome the first objection, he showed that objects in the air would stay with the moving Earth, the concept of inertia. He showed that the idea that objects naturally come to rest was wrong. He showed that objects will stay in their motion unless a force acts to slow them down. This was later Newton's first law of motion. And in this view, it's natural that the Earth spinning would carry the atmosphere with it, which would resist slowing down, and so we, going along with both us and the atmosphere and the planet we're on, would not detect our continuous motion. The fact that objects travel at the same speed and acceleration, independent of their mass, was finally demonstrated not until we went to the moon.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
I'm not going to argue that it was worth going to the moon and spending $100 billion just to do this experiment, but it's a pretty beautiful demonstration of Galileo's correct physics. The fact that objects of different sizes and apparent weights do accelerate at the same speed if you can remove all the other forces that are in play, which is difficult to do when you live in an atmosphere. The second objection was heavenly perfection. And Galileo, of course, completely nailed this one because he showed that comets, as Tycho had already showed, that comets and supernovae were not part of the heavenly perfection. But Galileo added sunspots, mountains, and valleys on the moon, and he removed the distinction between the Earth as a special place and the celestial worlds as different, special, and pristine. It's the idea of many worlds, which eventually is expanded into the idea that stars can have planets, and planets might have life on them, and so life on the Earth might be not unique. Galileo saw the four moons orbiting Jupiter, proving that not every object orbits the Earth, and his beautiful drawings on the left show how carefully he observed night after night as the four moons moved around Jupiter, mapping out their orbits. The third objection of parallax was trickier. Tycho thought he had measured stellar parallax, and the lack of parallax seemed to rule out an orbiting Earth. But Galileo helped to explain the absence of observation of parallax by showing that the stars must be much further away than Tycho thought. And if the stars were much further away, then the lack of a parallax was no longer so troubling, because the distance the Earth moves in its orbit of the Sun is probably a small fraction of the distance from the Earth and the Sun to the stars, and that means the parallax effect would be very small and perhaps unobservable. It turns out parallax was only observed in 1833. It took much better telescopes and observing techniques to measure it. Here we see the phases of Venus in a time lapse, and this was of course the pivotal observation that cemented the Copernican view, because you can see in the comparison of the two diagrams at the bottom that this is only possible in a heliocentric model, not in a model where all objects orbit the Earth at equal distance all times in their orbits. In Galileo's life, there are two phases, and we've come to the end of the first phase. Him as the founder of modern physics with laws of freefall and inertia, establishing the scientific method based on experiments, the ability to write his subjects up in popular media that could be circulated not just to his colleagues but to general people, And he finally came back to Florence, where the second phase takes over, which is his conflict with the church. And so we move into the situation where he's at the pinnacle of science, but he's still pushing the Copernican view, writing about it, and he starts to antagonize the church. And this phase ends, of course, with his trial in 1633, where he has to renounce Copernicanism and is sentenced to house arrest until his death. And that's the end of this topic.